Hello everyone. In the lecture today, we'll go through highway subgrade structure. Basically, we will introduce the requirement for the subgrade structure design and the potential factors affecting the behaviors of the subgrade structures. Here's a quick review about the highway pavement structure, which is a multi-layer structure with surface, base, subbase, and subgrade layers. We are interested in the subgrade layer in this lecture. Usually we know that the subgrade will have relatively weak and moisture-sensitive soil, and we want to do some treatment about the soil. To conduct that, we have to understand the potential requirement to the soil and the factors which will change the behaviors of the soil. This is the outline of this lecture. We will first go through the requirement for the subgrade design, and then we will review the factors affecting the subgrade behaviors, and we will then summarize the factors we need to consider for the subgrade design. We know that subgrade is the foundation of the pavement, so as a pavement designer, we have to consider the impact of the moisture, the freeze soil effect, non-uniformly strength, stiffness, and density of the subgrade soils in the design. The page here shows a wish list for subgrade design. First of all, subgrade should have sufficient bearing capacity so that it can support the upper pavement layers and the traffic load. Second, usually subgrade will have low deformability so that it won't cause any severe distress to the pavement. Third, we want the property of the subgrade to be time independent. In that sense, we can make sure that the pavement can last for a longer time. Also, the subgrade should not be susceptible to the environmental change, and it should have good drainage so that the pavement can work at different environmental and weather conditions. The first factor we want to consider is moisture or water contents for the soil. Actually, moisture content is very critical for fine-grained soil. Increasing the water contents will result in reductions of strength and stiffness of the soil, and also volume expansion. And this kind of expansion will be very significant for expensive soils. With the volume expansion, we will observe some severe distress on the surface of the pavement. In addition, the frost heave effect is highly related to the water contents of the soil. Sometimes the effect of the moisture on pavement performance is very complicated. For example, in hot weather, the water vapor will travel upwards and is collected behind the asphalt layer. And in that sense, the moisture contents of the soil behind the asphalt layer will increase, which will make the soil softer. With the softer soil, the strength and stiffness of the lower layers will be smaller, and it will increase the probability of failure for the pavement. The figure here actually demonstrates the impact of the water contents to the strength and stiffness of subgrade soil. Clearly, we can see that by increasing the water contents from 11% to 15%, the axial stress, especially the maximum axial stress, will reduce dramatically from approximately 41 psi to only 17 psi. In addition, the increased water contents will significantly increase the axial strength. This indicates that the water contents will actually have significant impact to the strength and stiffness of the subgrade soil. By increasing the water contents, the soil will become softer to support the pavement, and it can easily cause pavement failure. The water contents also have some significant impact to the resilient modulus. We actually showed these two figures in our previous lecture. By increasing the water contents from 4% to 8%, we can see that the resilient modulus will reduce dramatically for granule B material, while for granule A soil, the reduction is not that significant. And these two figures actually demonstrate that the resilient modulus is sensitive to water contents when the percentage of the fine particles increases. That's also the reason we observe significant reductions for granule B soil. The stiffness of the soil is also a function of water contents. From the field analysis, we can also see that the stiffness is a function of the compactive effort. The two figures here actually demonstrate the impact of the water contents and the compactive effort to the stiffness. The figure on the top shows the stress required to cause 5% strain, which is applied to measure the stiffness with respect to different foot pressure, which is applied to measure the compactive effort under different moisture contents. Here we can see that by increasing the foot pressure, the stress increased dramatically, which means the stiffness of the soil is increased dramatically. Moreover, for a fixed foot pressure, for example, if we take a look at the first one with the foot pressure of 276 psi, the stress at 11% moisture content were reduced from 5 to less than 1 at 20% moisture content. This indicates that the water content can significantly reduce the stiffness of the soil. In addition, we can also find out the dry density with respect to different compactive effort and water contents. Similarly, by increasing the foot pressure, the dry density will be larger. However, we will observe that the optimal moisture contents were reduced by increasing the foot pressure. In addition, for a fixed foot pressure, we can see that the dry density will increase when the moisture density is smaller, and this increase is actually caused by the lubricating effect. While when the water content is higher than the optimal value, then we will observe a decreasing trend for the dry density, and this is usually caused by the water entering the pore or the soil particles. In our previous pages, we showed that the water contents will cause significant issues for the expansive or swelling soil. Actually, the swelling soil is defined as the soil which are susceptible to volume changes under different moisture contents. It could either cause shrinkage or swelling for the soil. Usually, the magnitude of the volume changes for the expansive soils will be very different, and the trend with respect to moist contents will be different too. Usually, the expansive soil can lead to severe distress on the pavement surface. It could either cause the longitudinal crack near the pavement edges, or they can cause significant surface roughness along the pavement length. These two figures demonstrate the distresses caused by the expansive soils. The figure on the left shows the roughness caused by the expansive soil along the whole pavement surfaces, and the figure on the right demonstrates one longitudinal cracks caused by the expansive soil. Usually, we introduce a swelling potential to identify expansive soil. The swelling potential is determined as a percentage change in volume due to absorption of water. The equation here shows the method for us to estimate the swelling potential. It's actually the function of two variables, capital A and capital C. Capital A is the function of the plastic index and the percentage of the clay-sized particle, and capital C is just the percentage of the clay-sized particle, which represents this particle with the size smaller than 0.002 millimeters. Capital A is a pi over c minus phi, and for the swelling potential, S equal to A times capital A to the power of B times capital C to the power of 3.44. Here, little a and b are the coefficients for this equation. The values of A and B are different and different plasticity index. The table here shows the value assigned for letter A and B at different PI values. Based on the swelling potential and plastic index, we are able to categorize the expansive soils. First, if the swelling potential is less than 2 or the plastic index is less than 10, then the soil is categorized as non-expansive soil. For moderate expansive soil, the swelling potential is between 2 and 4, and the plastic index is between 10 and 20. While for the high expansive soil, the swelling potential should be larger than 4, and the plastic index is over 20. In Canada, most of the expansive soil is located in Saskatchewan, and in that province, we need to think about to add additional treatment for the soil so that we can remove the potential distress caused by the expansive soils. Now we can quickly summarize the distress caused by the expansive soils. In general, expansive soils cause pavement distress in two phases, swelling and shrinkage. Usually longitudinal and transverse cracking occurs when the subsurface flow of the moisture travels in one of the two directions and causes the vertical movements of the slab or the road. The second one, for block cracking, it usually occurs in the road and slab when a specific patch is introduced to the moisture changes. And this type of cracking can also happen in below-grade foundation wall if the flow of water is constricted between soil layers. There are actually a lot of treatments that we can apply to handle the issue caused by the expansive soil. First, we can simply remove or replace the swelling soil from the pavement, or we can partially or fully encapsulate the swelling soil so that we can reduce the changes in the subgrade moisture. The lime or cement stabilization is another efficient method for controlling the swelling of soil. For the soil stabilization, we will introduce them in our next topic. Frost and soil effect is another significant factor we have to consider in the pavement design. First, the first action will have a lot of issues for the pavement, including heaving, surface roughness and cracking, blocked drainage, and reduction in bearing capacity during soil periods. And the severity of this effect is actually determined by the type and the uniformity of the soil, regional climatic conditions, and the availability of water. The soil effect occurs on frozen soil. It's able to increase the water contents to the soil, which will further reduce the strength and stiffness of the soil. Usually, the most severe damage from the first soil effect happens in spring due to the loss of the base and subbase strength when soiling and excess water weaken the pavement layers. The two figures here demonstrate the damages of the pavement from the first soil effect. On the left, you can see the first heave and the roughness of the pavement surface. On the right, the first soil effect will also cause some cracking along the road. This one is usually caused by the uneven support from the subgrade layers, which is related to the first soil effect. Now let's try to understand the mechanics of first heave. First, we know that the surface tension of the pavement will increase with decreasing temperatures. At the same time, at low temperature, the capillary rate increases. It will bring more water from downward to upward. When the temperature is reduced to the freezing temperature, then the water in some large voids will freeze, and the ice in the voids will further suck water in and form large pockets of ice. The growth of the ice length is halted when the temperature is low enough to freeze the capillary water. Owing to the expansion of the water to the soil and the migration of the water to the zone of freezing, the surface raises, which will result in the first heave. Capillary rise is one major cause of first heave. The equation here shows the height of the capillary rise as the function of the grain size distribution and void ratio. Here, letter C is the coefficient, usually varies from 0.1 to 0.5 centimeter square. And D10 is the 10% particle size from the grain size distribution. Letter E is the void ratio, based on the property of the soil. We can also find and simplify the equation for the height of the capillary rise. It would be 0.306 over D10 over 5. The table here shows the typical height of the capillary rise under different types of the soils. For fine gravel with the grain size of 5 to 2 millimeters, the height is 2.5 centimeter. With a very coarse sand, for the grain size of 2 to 1 millimeter, the height is 6.5 centimeters. In general, with finer materials, the height of the capillary rise will be larger. Now let's make a quick summary about the required conditions for the first heave. First, the temperature should be able to drop to the freezing temperatures. And then the soil is first susceptible. Finally, there should be some available waters for the first heave. Usually the water table must be within the appropriate capillary rise zone. Groundwater level within 1.5 meters of the proposed subgrade elevation is an indication that sufficient water will exist for ice formation. While for the homogeneous clay subgrade soil, usually it contains sufficient moisture for the ice formation, even when the depth of the groundwater is exceeded for 3 meters. However, the magnitude of the influence will be highly dependent on the depth of the freezing front. For deep first penetration, the groundwater at even a greater depth could have an influence on heave. This figure demonstrates how MTO identifies first susceptibility for different types of soils. Basically, MTO utilizes the capillarity and the permeability of the soils for the identification. From the figure, we can see that only silts, silty sands, and very fine sands will have severe frost action. There are also many other definitions of frost susceptible soils. In the US, the Corps of Engineering defines that there should be no more than 3% of particles smaller than 0.02 millimeters for frost susceptible soils. They also clarified that no more than 2% of particles passing the number 200 sieve. However, this definition only relies on the grain size and is not well justified by the other studies. The figure here demonstrates the materials which are preferred by the pavement design to prevent the first heave effect. The white region represents acceptable materials, while the gray region are the unacceptable materials. Basically, the soil with a high silt content and a low clay content is not preferred by the pavement design. We should find out the soil which will fall into the white region. The table here shows the classification of frost susceptibility for different soils. Basically, we have 4 frost groups, F1 to F4. F1 means negligible to low frost susceptibility, while F4 indicates very high frost susceptibility. Different types of the soils will actually have different frost groups. Also, in the table, we can see the group definition with respect to the percentage passing through number 200 sieve. For different type of the soils defined by the USCS method, we can also categorize them into different frost groups. The figure here demonstrates the rate of first heave with respect to the percentage of the particle size smaller than 0.02 millimeters for different soils. The rate of the first heave varies from 0.1 to 30. It represents negligible frost susceptibility to very high frost susceptibility. In the figure, we can find out the ranges for the rate of frost heave for different types of the soils. The depth of the frost penetration is another important factor for the generation of frost heave. In Ontario, we can actually apply the equation here to estimate the depth. So here Z will be used in the unit of inches. Z is minus 12.8 plus 1.6 times the square root of capital F. Here F is the freezing index. It represents the degree days below 32 Fahrenheit. That is 32 minus capital T times the number of the days. For example, if we have 7 days with the temperature around 32 Fahrenheit, then we can find out the freezing index as 32 minus 22 times 7, which will give you the value as 70. In general, the frost penetration in southern Ontario is around 10 centimeters, but it can go up to 2 feet or more depending on the type of the soil. In northern Ontario, the depth is around 6 to 7 feet, which is about 2 meters. Particularly in Hamilton area, it's about 2 feet, and in Ottawa Valley, it's around 4 feet. The figure here shows the depth of frost penetration across the whole North America. In Ontario, we can see that the depth varies from 28 inches to 120 inches. There are many consequences of the first heave. We know that the first heave is caused by the formation of ice lines in the subgrade layer, and they will make the surface of the pavement very rough, which will reduce the comfort of the ride along the pavement. Also, due to the soil effect, the pavement will lose the strength to support the traffic load, and this will further increase the distress of the pavement. So that will be all about the lecture today. Thank you very much for your attention.